Hi, thank you, and thank you all for coming. I've been to a couple of conferences around the country, and we really thought that there was a need for something like this on this side of the country. The folks on the West Coast get a lot of attention when it comes to EVs, and rightfully so. But I'm going to speak a little bit about EV technology and standards this morning. It's going to be a very high-level conversation. I want to, qualify it briefly in that it's going to be technically accurate, I believe, but it is going to be broadly generalized. And I'm going to focus on EV technology, mainly because there's a component of EV in plug-in hybrids and in pure EVs and in extended range vehicles. So you'll see in a little bit why I'm focusing on that. I'm also going to use the Nissan Leaf as the basis for my explanations. The Nissan Leaf is the most popular pure battery electric vehicle that's on the road at this time. And it's an excellent example of EV technology. And the last thing I'll leave you with is that this technology is advancing very quickly. So as you begin to explore EVs and plug-in hybrids and all of the technologies that are associated with EV transportation, make sure you check in with the OEMs and with the standards development groups to get the latest information. A couple of things about EVs, they operate almost identically to a car in some ways. They have brakes like a regular car, steering wheel, and an accelerator, and they drive very similarly, but obviously they're quiet. But there are some considerations that you have to take into in advance, and that's like, where do I fill up? EV charging stations are not ubiquitous like a gas station, so there is some planning that goes into traveling and using an EV to do that. You'll need, essentially you're going to need a smartphone and an app. So there is some overhead that's associated with owning an EV that falls outside of the realm of simply owning and maintaining the vehicle. And another consideration too, and you'll hear a little bit about it, is what is the ambient temperature? And when we talk about that, we talk about the extremes in ambient temperature. In the desert or in the northwest or in the colder climates, you're going to get less range out of the battery. The battery is also going to charge more slowly. So there are some considerations there. Having said all of that, EVs meet the travel requirements of 95% of the drivers in the United States. Most of those folks that their commute is 28 miles on average in a given day. So even with the restrictions that you might run into based on the temperature that you're going to have to deal with, you're still going to find that an EV is an acceptable mode of transportation. And as I've talked to people here, once you've driven an EV, it's really difficult to go back to an internal combustion engine. Mechanically, EVs basically are a lot simpler. They don't have a radiator or transmission in them. So on the maintenance side, they're going to be a little bit cheaper to maintain, actually be a lot cheaper to maintain. When you get into hybrids, that's another animal there. And basically because you have two propulsion systems in there. You have an internal combustion engine or some type of motor in there, and then you have it work in tandem with others. So they do get more complex when you get in a hybrid environment. They also get more expensive because you have two propulsion systems as opposed to one. Benefits from the EV technology. There are huge reductions in greenhouse gases and particulate matter. EVs, pure EVs, are known as zero emissions. You will hear some debate about are they truly zero emissions, and that centers around what is the upstream contribution of greenhouse gases to produce the electricity that you use to charge these vehicles. In the Pacific Northwest, where you have hydro to greenhouse gases is going to be significantly lower than if you were charging an EV in West Virginia and using coal-generated power to charge your vehicles. So you'll hear some of those debates going on. The benefits of EVs are magnified hugely in an urban environment, and this is where I really see the greatest potential. And David Dunn and some folks from Orlando will be talking about this a little bit later, but imagine taking 5,000 cars in the mall parking lot that are sitting there idling and using fossil fuel and replacing them with EVs and having them idle. I mean, which environment would you want to be in? So the EVs in the urban environment have huge upside, especially in mass transit, taxis, and some other applications. And then also, EVs are inexpensive to fuel. They're about $1 a gallon. That varies. You'll hear from 85 cents to $1.15. But in general, also the cost of electricity over the last 3 or 4 decades has been really steady. So you're going to see a little economic benefit from driving an EV. Excuse me a second. Okay, so quick vehicle comparison. There's 4 variants basically. I use the Nissan Leaf as a pure battery electric. It's got grid charged batteries. It has a range of about 110 miles pure battery range. That's the 2016 model. The 2015 has a lower range. There is no gas-powered engine in it. It's electric motor and batteries only. Then you have a plug-in electric hybrid. That's Ford C-Max as an example. It has grid-charged batteries. It has a range of a pure battery range of approximately 20 miles. And it has a gas-powered engine that works alone or in tandem with an electric motor. You have the extended range Chevy Bolt. It also has grid-charged batteries. It has a range of about 53 miles, and it has a gas-powered generator that charges the batteries to extend the range. And then you have the hybrid, and it is a battery technology, but there's no grid charging that goes on in it. It uses a gas-powered engine and a generator to charge the batteries, and the electric motor works in tandem with the motor for propulsion. Wanted to show you a cutaway of the Nissan Leaf. You can see that the battery packs, the lithium batteries, are typically in the floorboard, or they always are in the Nissan Leaf, but this is typical of most manufactured vehicle layouts. It's an excellent place for the batteries, given the current form factor of the batteries, and also it lowers the center of gravity and provides good handling. Up in the front, you'll see there's the onboard charger, the inverter, the motors. You can't really see the detail here, but just to give you kind of a geography of the layout of an electric vehicle. The basic EV charging components. Starting on the right, have the EVSE, that's the electric vehicle service equipment, also known as the charger, and that comes in a variety of different flavors. I'll talk about those in just a second. And basically the EVSE is connected through a coupler or a connector to the inlet on the vehicle. There is an onboard battery charger also on the vehicle, and we'll talk a little bit about that in a minute. And then obviously there's the battery that provides the power to run the motor for the EV. Talk a little bit about the EVSE for a second. This is also known as the charger. It's connected to an electric power source, usually a grid power source. They provide AC or DC power depending on what the application is. And the important thing to remember is that the EVSE and the car are communicating constantly back and forth with each other. It's not like plugging in or sticking a conventional fuel pump in there and you just turn it on and let it go. There's a lot of communication that's going on between these two devices to regulate and properly manage the power flow into the vehicle. I have on here power output is important. It is from the perspective of if you have a 3.3 kilowatt battery charger on the car and you have a 6.5 kilowatt charger in your house, you're only going to be able to charge that vehicle at 3.5 kilowatts, 3.3 kilowatts. So you need to match those power outputs so that you can get the highest efficiency on the charging. Down at the bottom are three examples of chargers. The one on the left is the level 1 that comes with the vehicle typically. It plugs into any electrical outlet that you have in your house. Runs on 110. If you have a Nissan Leaf battery that's about 50% depleted when you get home, that charger will restore the charge to 100% or near 100% in about 8 hours. The level 2 charger is a 220 volt device. It takes the power basically that your clothes dryer does, so it requires a special installation. You do have adapters where you can plug them right into the home dryer outlet. It'll charge that 50% depleted battery in about 4 hours. And then the DC fast charger, that's a commercial grade charger that's usually installed in a public or commercial location, and that will restore your 50% depleted battery in the Nissan Leaf about 15 minutes. Okay, EV battery systems. There are two battery systems on EVs typically. There's the standard battery that we're all familiar with. It's used to power the display and some other auxiliary systems, but the main battery system in EV is the traction battery system. And you'll see some illustrations here. This is a complete Nissan Leaf battery pack at the bottom, on the bottom right, and then this is one of the modules that makes up that battery pack. There are 48 of these modules in that complete battery pack. The batteries are lithium ion, just like your laptop. And the battery systems are also known as RESS, or rechargeable energy storage systems. That's because you can take and export the power from the EV to run in an emergency situation with the proper connections and proper equipment. You can run your refrigerator, some of your house lights. So there's a lot of work going on how to use these battery systems in vehicle-to-grid situations and emergency situations. This will give you an idea of how battery size relates to mileage. And Nissan Leaf has got a 30, again, this is a 2016 Nissan Leaf, has a 30 kilowatt hour battery. It'll give you about 110 miles worth of range. The Ford C-Max is 7.6 kilowatt. You'll get 20 miles worth of pure battery range out of it. The Prius, again, this is illustrating how the battery system in a Prius, in a hybrid, is used to augment and provide better gas mileage to a conventionally fueled internal combustion engine. It has a small battery. It doesn't really spec in terms of what the mileage can be because it works constantly in tandem with the internal combustion engine. And then there's the Tesla, 85 kilowatts for the Model S, and it has about 265 mile range. Again, those are specific, but the ranges vary. I think one of the things that's really important to understand too about battery systems and EVs is the larger the battery, the more range, but at the same time, there's more weight that you have to haul around, so you get diminishing returns. And that's how the engineers, that's one of the big battles that they have to fight constantly. We talked a little bit about the onboard charger. It communicates with the EVSE during the charging process. In if you're using a level 1 or a level 2 charger, those are AC output. The batteries accept a DC charge. So the onboard charger will take the AC output of the level 1 or level 2 charger and convert it to DC to charge the batteries. If you're using a DC fast charger, the onboard charger is bypassed completely and the charge is applied directly to the batteries. And typically the onboard chargers are 3.3 kilowatts or 6.6 kilowatts. And again, that the 6.6, as I understand it, I haven't checked it in a while, but it's kind of an optional package for me. So it depends on what trim level you order on the vehicle. The inlet is really basically a plug. It comes in 2 flavors or 2 standards. The one on the left is the Chatamo. That's common to the Japanese vehicles and some of the European vehicles, and also to Mitsubishi and Nissan. The one on the right is the CV port for the J1772, which is the SAE standard, and that's a common standard for Ford, Chevy, BMW. I think Volkswagen uses the 1772 also. The connectors are operate very similarly, almost practically for all purposes. They do operate very similarly. They're based on different technical needs that the OEMs think that they need. This is kind of the VHS versus beta battle that some of you may remember from back in the days of, well, actually, really dating it, VCRs. Those don't exist anymore either. But in any event, these can be level 2 or DCFC, and it's important to remember that there are other standards. In this case, IEC, which is the International Electrotechnical Commission, which operates primarily in the European environment. They have a set of standards for their connectors, also for their couplers. And then Tesla has their coupler. So there's a variety of couplers out there. I've already talked about this, so I'll flip through this. EV motors, there's a variety of different motors in the vehicle, but primarily it boils down to the Nissan and the Chevy Bolt, for example, use a permanent magnet AC motor. That's considered to be a highly efficient AC motor. In the Tesla, you're going to see an AC induction motor. AC induction is considered to be a high-performance motor. So those of you who are familiar with the high-performance characteristics of a Tesla automobile will understand primarily why they use AC induction. It also has to do with the fact that Nikola Tesla invented the AC induction motor, so I'm not really sure that I understand that connection, but that's where they got the name. There are essentially 2 types of drivetrains that are in electric vehicles. One is a series, and that's simply where you take the propulsion systems and you put them in series, and they're either working together, they're working individually to provide propulsion, or you can have a parallel drivetrain, and that's where you have the EV on one side, the conventional propulsion system on the left side in this illustration. But the bottom line is they're still coupled, but they're arranged in a hybrid or in a parallel arrangement. Again, a lot of this goes back to what the engineers who are designing the vehicles, what they think their needs are. So they both work very well, but I just wanted to spend a couple of minutes to make you aware that there are a couple of different drivetrain engines. I wanted to spend a little bit of time on regenerative braking. It's kind of a misnomer. There is braking going on. Essentially what happens is, and the regenerative braking is the ability to recharge your batteries during the deceleration process. And so essentially what happens is you do apply the brakes, And I mean, there's calipers and there's C's, and so you are using brakes in the traditional sense. But when you do that, the onboard engine management system tells the engine to reverse and start spinning in the opposite direction, at which time it becomes a generator. And it's also, so it's generating electricity to recharge the battery in the braking process. I've likened it to engine braking. If some of you are familiar with that, we have a standard transmission. You downshift and you use the inertia from the engine to provide braking to the vehicle. So that's a brief explanation of regenerative braking. We'll talk a little bit about standards now. There are lots of them out there. We have a friend here that's visiting from the Canadian Standards Association, and we had a discussion about that earlier this morning. There are lots of standards that are needed for interoperability, and I'll go through a few of them here. I think this graphic from Bob Galen really illustrates what you're trying to do here, is you're trying to get all of these standards to mesh to get a vehicle that will operate properly. It can be manufactured and distributed across a number of different countries. And so you'll have ISO, IEC, SAE, UL, you'll see them there. So there's a lot. In the United States, the American National Standards Institute, or ANSI, coordinates EV standards development. And they do the coordination between UL, SAE, the Highway Traffic Safety Administration, and a lot of other groups that are developing these standards. The ANSI roadmap, the progress report and standardization roadmap for electric vehicles, is an excellent resource if you really want to know what is going on in standards development for EVs, and I mean everything from the charging stations to the batteries to just about anything. I would highly recommend that report. It's kept current, and ANSI is the coordinating organization for those standards in the U.S. Okay, so here's an illustration from Intertech that will show you where the SAE standards are applied. You got the hybrid battery safety, and over here you'll see abuse. That's basically their way of saying crash testing. Okay, so that's their standards for collision. Then they have the onboard battery charger, the inlet. We'll go through all of these, but you'll see another illustration in a minute that kind of illustrates how these standards from different entities are being applied over the same platform. I'm going to jump back a little bit here. This is complex because the standards groups do interact. We have the National Electrical Code, okay, and the National Electrical Code is the standard for how, basically, we'll say in this instance, how you wire the external wiring for the EVSE or the charger. And in particular, it's Article 625 in the National Electrical Code, but the important part of that is that Article 625 requires NRTL certification. And now, the NRTL certification comes from OSHA. And OSHA certifies nationally recognized testing laboratories. And they are the people who actually test and recommend manufacturing procedures for EVSE and for other EV-related systems. And probably the best well-known is Underwriters Laboratory. But Intertech Testing Services, as you've seen from the previous illustration, is heavily involved in that. There are also two other organizations I had mentioned, ISO and IEC. Okay, here's another illustration of how UL is involved in standards application in EVs. And you can see that, again, there is overlap. UL is involved in the EVSE environment. SAE is involved in that. So they don't carve out their own little piece of the standards. There is overlap between them. In some instances, it'll be for pure safety. In UL's instance and in SAE's instance, they set the standard for how does the auto shutoff work between the EVSE and the EV. In ULs, they'll talk about just the battery charger, what's the interface for that. But it's amazing that they work together, that they do, they get together. And once you've read the ANSI document, the roadmap, you'll see how well all of these organizations work together to achieve interoperability. Crash safety standards, National Highway Traffic Safety Administration is in charge of that, just like they are for every other vehicle. EVs routinely receive some of the highest crash test safety ratings, and Tesla has the honor of being the safest tested vehicle. And as far as EV accident recovery goes, the battery systems are well engineered and they are safe, but they are high voltage systems. And first responders do need to be trained in how to do recovery of an EV and do extractions. They routinely exceed 350, 400 volts. So somebody going in there with the jaws of life and cutting through one of those energized systems can be very dangerous. The fact of the matter is that there are automatic shutoffs in those systems, so if they're in a crash or if there's a short circuit, those systems are disabled. That's in theory, and it works 90% of the time, but as I'm sure all of you realize, there are considerations that first responders need to be trained in. A couple of additional standards, ADA applies here, especially when you're putting in a charging station. And then there are signage requirements that, they're not, I say they're not requirements. They're more or less regulated by local ordinance, but there are standards that are established by the Federal Highway Administration. I wanted to speak just a little bit about automated connected vehicles. We're seeing an integration of EVs into the automated and connected vehicle environment, and it's something that we think, and we've talked to some folks from the Department of Transportation, and they really see the EVs as being a crucial element in automated vehicles. Probably the most important piece of this is that a lot of funding is tied to this through MAP 21, and they have a 20-year horizon that they employ in their planning services, and these cars are going to be here well before 2035. So we need to get busy on that piece of it. I've included these for future references. You'll see I'm at the top. Mainly because most of my presentation came out of a report I did, and the report that I did was primarily to provide resources for people who would like to investigate the different aspects of EVSE in this environment. So you'll find a lot of the information that I talked about in that report, and at the end of it, you'll find a lot of references where you can go and get more information on this. The EVTC here is an excellent resource for information. There's the link for the ANSI report. Our friends at the Alternative Fuel Data Center, they have an excellent website for reference material for EVs and PHEVs and all of the variants of electric vehicles. We have some folks here from Clean Cities. They do a wonderful job in helping us get ready for EVs. And then, well, in particular, a guide to lessons learned from the Clean Cities. Clean Cities did, I guess they did 8 or 10 different projects around the country where they went into different cities and they analyzed how well they were ready for EVs. And these are the lessons learned from all of those investigations. So I think those are some very useful references. And I think that's about it. So, is there any questions I can help anybody with?
What are typical acceleration rates for EVs in general?
Well, a Nissan Leaf, you know, 0 to 60 is about 11 seconds or something like that. But if you're in a Tesla, it's going to be, I think it's on the order of about 4 to 5 seconds. So it's different. And also in the Nissan, if you have an eco mode in there. So when you're in eco mode, it's going to maximize the efficiency of the battery and the range of the battery. But if you want to go pure EV and get all of the instant torque that you get out of an EV, so if you're merging onto the interstate, you take it out of eco mode and it will surprise you. That's one of the things that people that tried EVs are they're amazed at the torque and the acceleration. Steve?
I heard somewhere that the level 3 fast chargers deteriorate the battery over time and reduce the range as they age. Are you true to that?
Yeah, there is, and that's true with all battery technologies, but it's marginal. There's, I think John Smart from INL, it would be a good guy to talk to about that. But in general, it's nothing to be concerned about. And that's one of the things the EVs are fighting against is there's a lot of credence given to what are just actually common occurrences. In this case, you know, the charging effect of the batteries, but it's negligible. It really is.
Doug, I just want to emphasize that on these fast chargers, at least like Tesla supercharger, which I'm well familiar with, there's a taper on the charge, which means that as the battery fills, it's slowing down the charge. And at the end of the charge session, the level 3 charger is not even functioning as a level 3 charger. It's functioning as a level 2 and even a triple charge towards the end. So it's only when you're at full charge that you're getting the most effect on the battery in terms of reducing battery life and by reducing the charge rate. And of course, as Doug said, the car is talking to the charger all the time.
The next presentation has some curves in this, so we're kind of jumping the gun a little bit. I didn't mention, excuse me, Doug, Doug was kind of presenting EVs from the automobile side. Richard Rostad, who is going to be on next, is going to really answer the questions that you're asking now. Let Richard do it, because then you can ask the questions when he's got some plots up which shows the effects that you're talking about both of them.
Just want to bid on those, I may have missed it. The slide presentations, yours, Doug, and the rest of them, are they going to be available to us after the conference?
They'll be available on the website on the evsummit.org. So we'll post all of them there as PDFs.
Thank you.